Okay, so let's start. Today we will continue with the photoelectric effect. Good. Questions? Photoelectric questions? Huh? Okay. Any questions you have? You?
I know. Suppose we have a cable.
Okay.
Flying along X and Y axis. Same cable. L-shaped cable. L-shaped cable.
Okay.
And a voltage difference applied on this cable.
What difference? Potential difference between a finite length wire.
Yes. But long enough.
Okay. Well, essentially you have a rectangular circuit. Yes?
A spaceship travels along the X direction. Ama şey olması lazım hocam. Tam o dik kabloya, dik kablonun noktasına doğru.
Okay.
Şimdi aşağıdaki kablo length contraction'ı vuruyor.
What's the speed? Some speed.
Some speed.
Okay.
Şimdi aşağıdaki kablonun direncinin değişmesi gerekmiyor. Rho L bölü A.
Is this the question?
Şimdi soru aslında kafamda biraz daha geniş ama aslında hata yaptığım için soru sadece bu olur. Resistance değişmesi gerekiyor gibi geldi bana. Öte yandan şey görmüştüm. Manyetik alan falan incelerken charge density'nin değiştiğini görmüştüm. Aynı zamanda akımın aynı kalması gerekiyor aynı kablo olduğu için. Dik geldiği için diğer kabloda length contraction olmuyor. Akımda Q bölü T. Bunu açıklayamıyorum işte.
Well, let's see. I don't know the answer, to be honest, but let's try to figure out what will be happening here.
Şimdi şöyle bir soru geldi arkadaşlar. Rho L bölü A ya. Rho değişiyor mu?
Maddenin yoğunluğu değişiyor length contraction.
Okay, let's see. So we have, this is how we define the resistance of an object at rest, essentially. But let's assume that, well, this is an assumption, let's assume that the same concepts we can use even if the wires are moving. This is an assumption, I don't know whether it will be valid or not. Let's say if you go to a different reference frame, what will change? Your friend says that, okay, this wire will be length contracted so that L will change. So the resistance of that part of the wire will change. So that's true. What about rho? What do you know about the resistivity of a material? Depends on? Depends on the material. What else does it depend on? Temperature. What else? Do you remember something like the mean free path?
Isn't the material enclosed there? Isn't the material enclosed there?
Well, yes. But let's write it explicitly. What do you expect? If the mean free path is larger, do you expect the resistivity to be larger or smaller? Do you remember what is mean free path? So it's basically a measure of how much, you see, we have this material, this conductor. There are the electrons moving around. Why do they lose energy? Well, they collide with the nuclei. But there will be an average distance that they can travel before they collide with something else. So that is what we call the mean free path of the electron. The average distance that the particle can move without colliding with anything, without interacting with anything. So if the mean free path is larger, it means that it's basically just moving almost freely. If it is smaller, it is constantly colliding with something and hence constantly hitting something. So the resistivity would be inversely proportional to the mean free path. But if the object is denser, then the mean free path will be smaller. So I can say that this will be the density. So the larger the density, the larger the resistivity of the material. So let's see what are changing. In this horizontal path, L doesn't change. L changes. What about A, the cross-sectional area? If you go to the reference frame of the ship, does it change? No. What do you expect about rho?
At that point, the question arose, does the density change when length is contracted?
Well, let's see, how do you define the density? Well, in fact, in this question, that density is not actually the mass density, but rather the number density. The larger the number of collision centers in a given volume, the larger the resistivity will be. So you can say that it's the number of atoms per volume. So does it change? The number of atoms doesn't change. Does the volume change? The volume changes. So rho changes, increases, right? Well, let's look at so does the resistance change? What would you expect? Well, their length is contracted. L becomes smaller by some factor. Rho gets larger by the same factor. So the product, I don't expect it to change. It should be the same. Let's look at the horizontal segment. Sorry, the vertical segment. L doesn't change. What about A?
Decreases.
A is contracted. What about rho? Well, let's see, what does it depend on? It depends on the number density. Number doesn't change, but the volume changes. Volume gets smaller because the area is contracted now. So rho increases.
So the electrons move at the upper direction, but the A decreases this way, and we kind of know that electrons move around the wire like that. But the mean free path, should the mean free path changes because the length contracted the sideways, not in the direction of the electron? Why does the mean free path changes?
Good question. Why does the mean free path change in this case? Does it change? So did you understand your friend's comment? He said that the mean free path, okay, on one hand, well, it's just some distance, some vertical distance in the vertical line. That length should be the same. It shouldn't be contracted.
I guess we can't really necessarily say that electrons move in vertical direction, but only their drift velocity is in that direction.
They actually move in every direction. They actually move in every direction.
Well, I mean, we are building a very simple model and trying to understand this question in this very simple model. So we can still say that on the average they will be moving vertical. I mean, we are looking at what this very simple model will tell us. Well, the problem over here is the mean free path is not just inversely proportional with the density, but it's, well, let's try to calculate it. I mean, I don't know if it was one of the last topics in 109. I don't know if you had studied it, but one of the simple means of estimating the mean free path is you just imagine a spherical molecule, let's say, or the electron. You can define an effective size of the electron. And then if your system is made up of, let's say, many such electrons, let's say this is moving with a velocity v. So if it has a radius r, you can imagine a cylinder around this, your particle, with a radius 2r, such that if the center of any molecule is, any other particle is within this cylinder, they will collide. So this particle will not collide with this one, but it will collide with this one. So if you want to estimate the mean free path, let's assume that it moves a distance t. During a time t, how many collisions will it make? Well, the number of collisions will be basically the number of other particles within this cylinder, which will become, well, the volume of the cylinder is 2r, pi times 2r squared. This is the cross-sectional area. The height will be the number of collisions. The height will be v times t in a time t. And the number of other molecules inside this volume is the density. Well, this is the volume times the number density. This is the number of collisions in a time t. Now, the mean free path would correspond to the case when this is equal to 1. Just one collision on the average. Well, this is our mean free path. So lambda is 1 over n times pi times 2r squared. So basically, on one hand, yes, n becomes larger. But now this cross-sectional area, it is horizontal. Let's see. You see, in this vertical column, we have this cross-sectional area moving upward. That area will also contract. N will increase by the contraction factor. Area will decrease by the contraction factor. So lambda, this product will be invariant. So rho will not change. So rho does not change.
How are we able to say that the n changes and the area also changes, but changes equal?
Well, you see, n is n over v. The total number of particles in a volume v. Well, the volume will be contracted in one dimension only. So volume v will just go to 1 over gamma times v, since it's contracted. L, if there is a length contracted, it will also go to 1 over gamma times L. Now let's see. The area, well, depends. What is the orientation of the area? If the area is moving upward, let's say, you go to a reference frame which is moving horizontally, then only one dimension of the area is contracted, so the area changes by the same factor, 1 over gamma. If the area is moving horizontally and you start moving like this, the area doesn't change.
Doesn't the radius changes with the gamma factor, but area is the square of that?
You see, you start with a disk. Let's say there is a disk sitting flat, and you go to a reference frame which is moving fast. then in that reference frame, it's no longer a disk, it's an ellipse. With one axis, still the radius, the other axis being contracted. The area of the ellipse is just the pi times the products of these two axes.
So the change of the, is it possible to say that the change of the area is equal to the change of the,
well, the change in the volume is always the change in the length. The area depends on the orientation of the area. Well, the length also depends on the orientation of the length.
and what about the collision, number of collisions?
Number of collisions, well, there is the other question of the number of collisions per unit time. If you go from one reference frame to the other reference frame.
I mean, my question is that how can we exactly say that they would be equal?
Which ones?
The changes. One increases, the other decreases.
Well, you see, just imagine this is my area. Let's say, and this is my length. Assume that these are in one reference frame, they are the same. Well, actually, it's just the one length. They can be overlapping even. If they are overlapping, they will be overlapping in every reference frame. If you go to a reference frame that is moving in this direction, you see, on one hand, this length will be contracted. This length will not be contracted. So it's a rectangle. The area is just a product of the two sides.
Yeah,
One side is...
What about collisions?
What?
Number of collisions.
Well, the number of collisions, as I said, is a different problem. Basically, the question is the time. You see, the number of collisions will not change, but the number of collisions per unit time will be different. You see, for example, in this problem, the current, will they be the same in every reference frame? No. The current will be different in different reference frames.
But the whole current should be the same.
Hmm?
The current on the same wire should be same in every part of the wire.
Why? Hmm?
If it's low enough,
The one thing is, you see, when you are saying that the current should be the same at every point on the wire, you are saying that there is no accumulation of charge. The wire will not be charged. But in the different reference frame, it becomes charged. Well, it will still be the same, but your friend had a question. No, you see, this is just a very simple model. Hold on. So, which you are complaining about the rho is proportional to that thing, or n is equal to capital N over V? Well, you see, I made a correction over there, though. Rho, I said that rho is proportional to 1 over the free length, the mean free length, where the mean free length is this one, in this very simple model. So this would be a more precise estimate of the mean free path. Now, what is the temperature dependence over here? Well, mainly the density will be changing. And the density will be changing. How do we define this size? I mean, we didn't really specify what this size is. We are defining some effective size for the electron that's moving around. That will also change with temperature.
so there are too many variables.
Yeah.
So
And plus, what do you mean by temperature of an object that is moving at relativistic speeds? Well, you see, the problem with defining the temperature for such systems will be, one problem is we have already seen the Doppler effect, and we have seen the blackbody radiation. One way to determine the temperature is using the blackbody spectrum. So the temperature of an object will change. That is, the blackbody spectrum that you receive from an object will change whether you are moving towards the object, away from the object, etc.
So in order to say, like, state anything, you should give numerical analysis. That's what we are.
Yeah, I mean, we shouldn't be just doing an analysis at the level that we are doing here. You see, for example, if you have two objects at the same temperature in one reference frame, they need not be at the same temperature at a different reference frame. Plus, their temperature need not remain constant. So just like the mass, we define the mass of an object as a property in its rest frame, let's say. We also define the temperature of an object as its temperature in its rest frame. So as to make sense to the term temperature. So you first go to the rest frame and then measure the temperature there. Other questions?
While explaining the homework answer about the inelastic collisions, you said that in one reference frame it is possible to see dissipating heat as sound or something else. Are there any real-world examples for such an event?
What do you mean by real-world examples?
Did we ever observe two different types of energy from same event by two different observers? For example, can my voice...
Well, let's see. If you talk about the voice, nobody heard your voice while traveling at speeds close to the speed of light. So there is no practical application of that. The only thing we did was collide particles at speeds close to the speed of light. And then there's practically no internal energy change. You see, if you ask me for practical examples of these phenomena, one practical example that we had studied was the magnetic effect. That was a practical case, where although the relevant speeds were very slow, they just build up to create a magnetic field or an electric field in a different reference frame. And we had also seen that the both descriptions in the non-relativistic limit, they match, although we are using relativistic length contraction. Other than that, for practical speeds, the only thing we observed was, let's say, atomic clocks moving in orbit and on Earth. And the difference was less than a second for the difference in several years. I think it was less than a second. And the other example we had studied, we have been studying we actually tested the prediction was in particle physics, where you don't have internal structure. Well, the internal structure is more or less fixed. Okay, now photoelectric effect. Now this is the experiment we are doing. So we basically have a vacuum tube. On one hand we have some metal. On the other hand we have another metal. We create apply a potential difference so that this side is negative, this side is slightly positive. And you apply a potential difference, let's call it V0. And the observation is that if you, in the experiment, we are dropping some light on this metal. Now, what are the variables we can control in this experiment?
Voltage.
The voltage. The intensity of light, the metal, I'm sorry. Just imagine, we don't know yet anything about the photons, the frequency of light. So these are the parameters that you can measure. And you will do the experiment. You will devise an experiment. What will you measure? We will measure the current. Let's put an ampermeter over here. Let's see. You measure the current as a function of, what would you like to change? Frequency.
Solda yazdığınız I intensity.
No, this is intensity. Well, let me call this I, small I. Well, as you change the frequency, how does the current change? Do you know? Well, so what's the kinetic energy of the electrons? Okay. Well, we don't, let's say that, okay, as the observation is that up to a given frequency, there is no current, whatever you do with the intensity. And beyond that current, you start to get some, beyond that frequency, you start to observe some nu zero, some current running through your system. Well, if you increase the intensity, the current becomes larger. If you lower the intensity, the current becomes smaller. This is one observation we have. And then we have, of course, this is assuming at a given V0. So whatever the intensity is, the current only starts appearing at a given value of V0, nu zero. So that's another parameter which we can control. That's another the current is an observable. So you see, we are measuring the current, so we are making an observation. Another observable now appears to be nu zero. How does nu zero depend on the other parameters in our problem? So let's see, nu zero as a function of, let's keep the metal the same for the time being. Nu zero is a function of the voltage, V0. As V0 gets larger and larger, well, even for very small V0, there is some nu zero. Even V0 is 0, there is some nu zero that you need. It's non-zero. As you increase V0, nu zero increases linearly. So this is what we see. Again, experimental measurement. And this is independent of, or let's say for all intensities. No matter what you do with the intensity of light, this doesn't change. You see, even in, that's what something we saw over here. So for various intensities, the current is larger for larger intensities, but the frequency at which we start to see the current is the same. And then we can look at I as a function of the intensity of light. And as the intensity of light for a frequency which is able to create the current, and they turn out to be linear. The larger the intensity, the larger the current you have. Now, another observation is how long does it take for the current to start? You turn on the light And how long does it take for the current to start? How long does it take before you start measuring a current? And the observations told us that it is very small. Let's say less than 1 second. Almost at the instant that you turn on the light, you start observing the current. Now let's make an estimate. Classically, forget about quantum physics, forget about the photons. Let's see, okay, let me pick up some numbers from your book. Yes?
Does these graphs extend indefinitely?
Well, let's see, can you create an infinitely high frequency light?
No, I meant if we increase the light intensity to some certain number, is there a region where it stops to be so?
Well, let's say within the measured range. You see, when you are doing an experiment, you're always measuring within a finite range of values. You don't really know anything beyond that. So within the measured range of intensities, this turned out to be linear. Will it go on indefinitely? Well, it cannot go on indefinitely. If the intensity is large enough, you will start melting the metal. You will break your equipment eventually. So in that case, of course, you cannot measure this linear dependence. Well, in your book, there is this example of the photoelectric effect where you'll use a light of wavelength 350 nanometers. This is a UV light. And intensity is 1.0 watt per meter squared. Now let's see. You are sending this light beam on, let's say, some kind of a metal. And then what will be the intensity of light falling onto an atom? Yes, eventually what you see is the material is made up of many atoms. This intensity, 1 watt, is spread over 1 meter squared. The electrons are inside the atoms. Let's make the very simple idealization that an electron in an atom just acquires all the intensity of light falling onto that atom. That will be a very simple approximation. So what is the intensity, what's the total power falling on an atom? How much energy falls on a single atom per second? What is the area of an atom? Well, this is I times area. So it's 1.0 watts per meter squared times pi. What's the typical radius of an atom? In meters? 10 to minus 10. Squared. So this meter squared will cancel this meter squared, so we end up having 10 to the power minus 20 watts. Well, let's say how much does it change this number? You see, I already ignored that pi, which is 3. Okay, so what would you expect this number to be, larger or smaller? Smaller. So it's making the power even smaller. So you can say that this is an upper limit on the power falling on the atom. And plus, we are even making the approximation that all the power falling on an atom will be absorbed by a single electron. This is at most it can absorb. So this, you can think of it as an upper limit on the power absorbed by the electron. Now, it is also known that the energy, the energy of the electrons You see here the experiment is typically light falls on the metal. It will liberate the electrons. The electrons will be distributed in every direction, not in a single direction. They don't necessarily have the same kinetic energy, but the upper limit for the kinetic energy of the electrons here will be all the energy of the light. And some of them will move in this direction. And if they are able to reach this other electrode, they will close the circuit and you will measure a current. But of course, this potential, this stopping potential, will try to prevent the electrons. So if you see, this is the negatively charged electrode. So as the electrons are moving in that direction, you are stopping them. You are slowing them down. And basically, by measuring what is the stopping potential, what is the potential needed for the electron to stop completely, you just increase V0 until all the current stops. That gives you the typical energy of the electrons, the kinetic energy of the electrons over here. And that energy is known to be a few electron volts in this experiment. So energy of a typical electron well, again, that is not an exact number. It can be 2 electron volts, 5 electron volts, but typically at the order of electron volts. How many joules does that make? 1.6 times 10 to the power minus 19 joules. So on one hand, we are inputting this much power. On the other hand, an electron needs this much joules. How long does it take? What was the power? What is the watt? Joules per second. So you see, we are inputting 10 to the power minus 20 joules per second. And we need 10 to the power minus 19 joules for a single electron to be released. How long will it take? Typically 10 seconds. So basically, this approximation tells us that we need 10 seconds for the electrons to start being released by the metal. But it just doesn't happen. The moment that you have the light, you start seeing these photoelectrons. So in a sense, this power, 1 watt per meter squared, cannot be just uniformly distributed over the whole area. It should be concentrated so that the electron can acquire all the energy it needs just at once. So just like if you remember when we were discussing the blackbody radiation, we said that the blackbody radiation, at least Planck's explanation of the blackbody radiation, required that electromagnetic field can only acquire energy from the oscillators of the walls in some energy packages. And this photoelectric effect tells us that the electromagnetic radiation, which is nothing but the light, can also give energy in packages, not distributed, but there are just these localized packages so that the electron in this photoelectric effect can acquire one package, all of it or none of it. If it acquires all of it, then you have a photoelectron. It's liberated and it goes on. Now, any questions on this one? So let's see how this description of the light in terms of packages explains all this phenomena. You see, now the picture we have is light is a collection of photons. and photons of frequency nu has energy h nu. So the idea is, let's start with the existence of this nu zero. So you are sending your photons on your metal. In your metal there are all these electrons. And since you are sending energy in packages of h nu, the electron can acquire that, it can absorb that energy h nu or not. That's the only thing it can do. It cannot just absorb half of it, or it cannot absorb two of them at the same time. It either absorbs one and is liberated, and then, or not. But if the energy of that photon is very small, you see, we have the metal. Why are the electrons inside the metal? Essentially, the metal makes a kind of a potential well. There is a well created by the metal itself, by all the other charges in the metal. So the electron cannot leave that potential well unless you give it enough energy. You see, this would be a very simple example of a metal. This is the U is equal to 0 potential energy range, and we have the electrons inside having various energies. So unless you give an electron this much energy, then the electron will still be trapped. And that energy is called the work function of the metal. Phi is just h nu 0. So if the frequency of your light is large enough so that the energy of a single photon is larger than this depth, then the electrons close to the surface of this well, the electrons that have the highest energy in this well, when they absorb this photon, they will have a higher energy, and hence they will just go out of the metal. And you start absorbing the photoelectric current. Why do we have this dependence? Well, the intensity now is just a measure of the number of photons. If you increase the intensity, since each photon has a given energy, the change in the increasing intensity means you are sending more energy per second, but that means you are sending more photons per second. So as you increase the intensity, you send more photons, so each one of those photons can liberate one electron, and hence, if you send more photons, you will be liberating more electrons. So if the intensity is low, you don't have much photons, you have a few number of photons. Even if each of them liberate one electron, you will have a few less number of electrons liberated. If you increase the intensity, you are sending more photons, and since you are sending more photons and each photon is liberating one electron, you will have more electrons, increasing the current. Let me make a small correction of the work function. This is when V is equal to 0. Well, when V0 is increasing, why do we need a larger and larger frequency photons? Well, again, you see, when the photon is liberated, if you send a photon of a frequency nu, this much will be used to liberate the photon. So this is how much the potential energy changes. Plus, you have the kinetic energy. Well, let me write Ka max. This is the maximum kinetic energy that the electrons have. Why it is Ka max? Well, you see, when you send the photon, it can liberate an electron on the surface, so that phi of it will be used to overcome this potential barrier. The remaining will be the kinetic energy. But it can also liberate an electron that has this much energy. A larger portion of it is used to liberate, a larger portion will be used to overcome the potential barrier, and the smaller it will have a smaller kinetic energy. Not all the electrons will have the same kinetic energy. Okay, so given a photon of frequency nu, this is phi, this is the maximum kinetic energy of the electrons. How can we determine the maximum kinetic energy of the electrons? Well, you increase V0. You increase V0, then when the light falls on the metal, it will liberate the electrons. They will have a distribution of kinetic energies. The slower electrons will be stopped by a small potential. The faster electrons will need a larger potential to be stopped. So as you increase V0, the current will start to will get smaller and smaller, and eventually for a given value of V0, it will be enough to stop even the fastest electron. The current goes to 0. So when you reach that value of V0, that determines the maximum kinetic energy of the photoelectrons. Now, Ka max, the kinetic energy max, will be equal to the stopping potential. So if we go back to our plots, well, the kinetic energy max will be proportional to nu. And the current will be proportional to the speed of the electron, not their kinetic energy. So that's why it's not a straight line. But instead of plotting I as a function of nu, if we would plot, well, it's basically this one. What I call V0 is the maximum kinetic energy. If you plot stopping potential as a function of nu, it will be linear. This is E times the stopping potential. Okay, so we already explained, by assuming that the light is made up of these particles called photons, we could explain this behavior. Basically, the energy of each one of the particles should be larger than this work function of the metal. And if you change the intensity, you are changing the number of photons, and which will be changing the number of the photoelectrons. If you come here, if you have a larger stopping potential, initial kinetic energy max should be larger, which means the nu zero should be larger. So this linearity we can explain. And this is just the fact that the current is proportional to the number of photons. Number of photoelectrons, which itself is proportional to the number of photons, if you can create a current. So basically all these observations can be explained by this photonic nature of light. Question? Well, I would say, you see, the current, how can you define the current? The current will be the number density times the charge times the speed. This is the current of a charge distribution, let's say. Whatever the charge, if you have a moving charges or charges that are moving around, so this will be your current. So E is constant. The number density is related with the number of photons rather than the frequency. And the velocity, well, if they are non-relativistic, for a few electron volts they will be non-relativistic. So the speed will be just twice the kinetic energy divided by the mass under the square root. Well, it won't be just this is not just a simple square root of some number minus the h nu times some other number. It will have a more complicated dependence, but nevertheless, this gives you an idea of how it should behave, more or less. Well, then you can ask, what happens if the voltage is such that the electrons move close to the speed of light? Well, then this system will probably not work anyway. You will not be able to measure anything. Yes?
In the book, it says that these photoelectrons are not the electrons that are from the atoms of metal, but they are free electrons on the surface. What is the difference between them?
Well, let's see. This is your metal. Let's say it has a thickness of 1 kilometer. And you send light. How far that light can go in? Less than 1 millimeter. The skin depth. So all the electrons over here are unaware that there is light falling onto the metal. So you cannot liberate them. Even if you would liberate them, let's say, well, an electron over here should travel all the way to the surface to get out of the metal. And on the way, it will lose its energy. So only the electrons on the surface can be liberated to a high precision, let's say. The probability of liberating an electron that was over here is negligible. And those electrons, are they the electrons of the atoms or not? Well, you see, the description of a metal is, most of the time, you have this, let's say, the core. There are electrons very close to the nucleus. They are fixed. They cannot go anywhere. But then there are the other electrons at the outermost shell. They are not really inside the metal, at least. They are not attached to a particular atom. So if you also have these electrons that are just moving freely. Almost freely, let's say. Now, to liberate these electrons, you need much larger energies than the ultraviolet light or the visible light can provide. You can only liberate these ones.
Is it the reason why we don't talk about any chemical change in metal by ionization?
Why should there be any chemical? Well, you see, we do talk about, we can talk, what do you mean by the chemical properties of the metal?
If the light were liberating electrons inside the atoms, its net electric charge should change. The chemical or physical properties of the metal should change. But this does not cause any change like this.
Well, let's see. Let's go back to the sketch. Why do we have a closed circuit over here? So that nothing becomes charged. So you see, let's say if you liberate an electron, let's say for an instance, you liberate an electron at a distance d. Well, then it will act as if there is a plus charge on the other side, d. So unless you get rid of that plus charge, you are not liberating anything. So that's essentially why we have a closed surface. You see, here there are lots of metals. On your phones, on your pens, And the visible light can liberate the electrons. But they're not losing electrons because they're just pulling them back. Because if they lose one electron, they become charged.
Hocam pozitif metale, ışığı pozitif metale düşünmemizin herhangi bir sebebi var mı?
Well, you see, the idea over here is we are trying to stop the electrons. And we are trying to measure how much voltage difference we need in order to stop those electrons. That is what we are looking for. That is something we can measure.
Eksi ucuna bir tane katran saksaydık ne olur mu?
Well, let's give a break and we can continue with these questions during the break.